So second problem is what? You have to find out once again the expression for displacement for a uniform bar subjected to axial uniformly distributed load. Okay, so this kind of problems you are not done in mechanics of material. So I'll show the diagram. So this is my uniform bar, once again fixed at one end. See, this is my uniform bar fixed at this end, and now it is having a length L. Same thing, it is having a length L, and it is subjected to uniformly distributed load, axial uniformly distributed load. So this is what we call it as an axially uniformly distributed load. Let us consider it as a Q naught. Q naught per unit length. Q naught per unit length. And this bar is once again having an Young's modulus E and cross-sectional area A. So this is the representation of axial uniformly distributed load. Now it is not, this bar is not subjected to point load. Now it is subjected to uniformly distributed load along the length of the bar. Now I need to find out, because of this uniformly distributed load, what is the extension in this bar. There will be some extension. This is, let us consider this is the extension. So I need to find out what is this extension in the bar because of this uniformly distributed load. Now how to solve this problem? Same 5 step. What is change here? Work potential changes. As it is a bar, strain energy is same. Therefore first step is formulate P function. So how to formulate P function? Pi is equal to, it is strain energy plus work potential. So we know that strain energy for the bar is given by EA divided by 2 integration 0 to L du by dx whole square into dx. This is the strain energy in case of bar. Now only thing is I need to find out the work potential. How to find out the work potential? It is force into displacement. So what I will try to do here, so let us consider a small element here. Let us find out first what is the work potential for the small element. Then I can do for the entire bar by putting the integration. So let us consider a small element having a length dx. Now what is work potential for element? It is force into displacement. As I have considered element at any random distance, let us consider the displacement at this at this location is u. I don't know what is the displacement, but what 100% I can say, I'll be having a maximum displacement here and I'll be having a zero displacement here. So now I need to get the work potential for the element. So I have considered element at any random distance. There I don't know what is the displacement. So let us assume it as u. Now how to get the work potential? It is force into displacement. Now how to get the force? As it is a uniformly distributed load, how to get a point force on this element? How to get a point force? How to convert UDL into a point force? How to convert UDL into point force? It is that force into distance. So force is Q naught, distance is dx. Therefore Q naught into dx is the force, UDL converted point force on that element, and work potential is force into displacement. Displacement is u. So Q naught into dx is my force and u is the displacement at that whatever the element I have considered. This is the work potential for that element. Now I want work potential for entire bar. So entire bar 0 to L, it is Q naught into u into dx, or Q naught into, or one more step if you want, if you need to write. So this will be Q naught into, what is that? Q naught into dx. Q naught into dx. This is my force into u. Now I put the integration from 0 to L along the length of the bar. So this is my entire work potential. So slightly I'll modify here 0 to L. I'll put Q naught into u into dx. Only this u I'll take it first. Then with respect to dx, I have to integrate. Therefore, I'll keep this dx at the last. So this is my equation number 1. Strain energy, it is equation number 2. Now, as I told, strain energy for the bar, it is fixed. Only work potential changes. Now I obtained the equation for work potential. This is my equation number 3. Now what I have to do? I have to substitute this equation number 2 and 3 in equation number 1 to formulate the PE function. That is my first step. Therefore, phi is equal to, it is EA divided by 2 integration 0 to L. It is a du by dx whole square into dx minus, see, as I told, my work potential is always negative. Please try to put this work potential is negative because my force is acting upon the system. Therefore, my work potential is negative. Therefore, it is minus integration 0 to L Q naught into U into dx. This is my entire PE function. Now, this is my first step. If I formulate this much, my first step is over. Now, what is second step? What is second step? I have to assume trial displacement function. I have to assume the trial displacement function. So here once again, U is equal to, same. In the previous case, as I told, in this problem, I ask you to assume a trial displacement function up to second order. And with that second order, I have obtained the desired displacement equation, that is PL divided by AE. Therefore, second order is sufficient. No need to go up to third order. In the second problem also, as it is related to bar, I'll consider up to second order. Therefore, it is A0 into, A0 plus A1 into X plus A2 into X square. So, second order polynomial function I am going to consider. Now, what second step says? Whatever the displacement function you are assuming, it should satisfy the given boundary condition. Now, same boundary condition I have once again here. When x is equal to 0, I have 0 displacement. That is my u is equal to 0. So, in the above equation, I have to substitute wherever x is 0 and wherever u is 0. Therefore, what I am going to get, 0 is equal to A0 plus A1 into 0 is 0 plus A2 into 0 is 0. Therefore, I'll get the value of A0, which is equal to 0. The first constant value I have obtained by substituting the boundary condition. Next, I have to substitute second boundary condition. When x is equal to L, u is equal to u1. Or you can also consider it as an umax. No problem. See, instead of umax, I have considered it as an u1. You can also consider it as an umax because you know at the free end, in a bar, at the free end, fixed at one end, when it is another end is having free, there I will be having the maximum displacement. So that either you can consider it as an u1, any notation, or umax. Therefore, once again in this equation, wherever u is there, I need to substitute it as an u1, and wherever x is there, I have to substitute as L. In the previous step, I obtained A0 is 0, therefore I will not consider this term. Therefore, my u will become u1. A0 is 0, A1 as it is, x is replaces with L plus A2 into L square. So this is the expression for maximum displacement, where once again I have to find out the value of A1 and A2. So I need to find out once again the value of A1 and A2. When I substitute that value of A1 and A2, I'll get the maximum displacement which is there at the free end. Similarly, if I want to consider at any random distance, when x is equal to x, u is equal to u. Therefore, u is equal to, it is A1 into x plus A2 into x square. So this is equation for maximum displacement. This is the equation for maximum displacement, and this is the equation for any displacement at any random distance. Random distance displacement. So this is the expression for random distance displacement. This is the expression for maximum displacement, and it is there at the free end. And this displacement is there at the free end. My trial displacement function satisfies the given boundary condition. Next is what I need to substitute this trial displacement function to PE function. That is my third step. What is third step? Substitute displacement function into PE function. So what I am going to get? Pi is equal to EA divided by 2 integration 0 to L d by dx of u. What is my u? I have u here. This is my u, which is a1 into x plus a2 into x square. So let us substitute that. It is a1 into x plus a2 into x square whole square into dx minus integration 0 to L. Second term, I have integration 0 to L q naught into u into dx. Q naught is constant, which is free from any x term. Therefore, I'll take it outside the integration. Therefore, here it becomes q naught outside. U, what is u? Once again, u is your a1 into x plus a2 into x square. This is my u into dx as it is. Now, see, whatever the first term, the simplification is same what you are done in the previous problem, because in the previous problem also my first term is same, no? See here, in the previous problem also my first term is same, EA divided by 2 integration 0 to L d by dx of u whole square everything. So that I have differentiated, substituted, expand with a plus b whole square, then I have integrated, applied the limit 0 to L, further simplified. Correct, no? So the first term, that means from this term up to this point, the simplification is same, only there is a change in the simplification in the second term, because this term which is not there in the first problem. Only thing is I need to integrate this. What is that simplification of this you obtained? What is the simplification of this term you obtained finally? Here. What is the simplification of that term finally obtained before minimizing? This is the equation. This equation you can directly write there. Or you can do simplification once again as a practice. Okay. So you expand this with a plus b whole square, then you integrate, put the limit, you come to that equation. So I will show only this simplification. So q naught as it is outside. Now I'll integrate this. So a1 as it is, integration of x is x square by 2 plus a2 as it is, integration of x square is x cube by 3. Put the limit 0 to L. So once again, both the terms are consisting of x. Therefore, I will not substitute lower limit. I will substitute only the upper limit. Q naught outside as it is. It is a1 into L square by 2 plus a2 into L cube by 3. Then in the next step, I will take this minus q naught outside. Inside the bracket. Therefore, it is minus q naught a1 L square by 2. Then minus q naught a2 L cube by 3. Therefore, what is my final P function? Pi is equal to, it is EA divided by 2 into this term. What is that? A1 L square plus 4A2 L cube by 3. So it is A1 L square plus 4A2 L cube by 3 plus, what is that next term? 4A1 A2 L square by 2. 4A1 A2 L square by 2 minus q naught A1 L square by 2 minus q naught A2 L cube by 3. This is my simplification. First term is A1 square into L. A1 square into L. It is A1 square. That simplification you do it. A1 square into L. A1 square into L plus 4A2 L cube by 3 plus 4A1 A2 L square by 2. Correct, no? And this work potential simplification I have done here, that I have kept it as it is. This is my third step. What is my fourth step? I need to minimize P. The fourth step is minimize P. Here I have two unknown. That is d pi by d a1 is equal to 0. And one more is d pi by, dou pi by dou a1 and dou pi by dou a2. is equal to 0, because in this equation I have two unknowns, that is A1 and A2. So those are things I need to find out, because my U1 equation consists of this A1 and A2. So these two constants I have to get in the form of known values, that is area, Young's modulus, length, applied force. In terms of that, I need to get this value of A1 and A2. Therefore, I am minimizing the PE with respect to A1 and A2. I mean differentiating that PE function with respect to A1 and A2 I am doing. So if I do the equation, this equation with respect to A1, what I am going to get if I do with respect to A1? So it is EA divided by 2 into A1 square L is there. So therefore it will become 2 A1L plus this term is A2 constant. Here it is 4 A2 L square by 2. So it is 4 A2 L square divided by 2 minus, here A2 is constant, therefore this term will be get eliminated. Left out with this term, differentiating with respect to A1 is 1. So it is Q0 into L square by 2. So this is Q0 L square divided by 2 is equal to 0. This is my first equation. Then second is differentiating same P function with respect to A2. So what I am going to get? Here A1 is constant, therefore this term will be eliminated. With respect to A2 is 1, so it is 4 L cube by 3. So here I'll get 4 L cube by 3 plus here A2, with respect to A2 I have to do. Therefore it is 4 A1 L square by 2. So it is 4 A1 L square divided by 2 minus, now here the A1 is constant, therefore this term will become 0. Now A2 is 1, so it is Q0 L cube by 3. So here I'll get Q0 L cube by 3 is equal to 0. What is next? Next I will simplify this by taking this EA by 2 inside the bracket. When I take EA by 2, this 2 will be get cancelled. So I have EA A1 L. Then similarly, when I take EA to this term, here it is 2 into 2, it is 4, and that 4 it will be cancelled with this 4. Therefore, I have plus EA A2 L square minus Q0 L square divided by 2 as it is equal to 0. This is first equation after simplification. Similarly, this EA by 2 also I'll take it inside the bracket. Here, if I this is A2 square. Correct, na? Here, A1 square into L plus 4 A2 square L cube by 3. So that square I have missed here. So this is 4 A2 square L cube by 3. If I differentiate with respect to A2, the 4 as it is, the differentiation of A2 square is 2A2. So this is 2A2. Shall I write it once again? So here, what I'll get it, after differentiating with respect to A2, 4 as it is into 2A2. What is that? 4 as it is, differentiation of A2 square is 2A2, L cube by 3 as it is. This is L cube by 3. Okay, now this is correct. So that instead of A2 square, I have only considered A2, therefore it has become mistake there. So that you can note down and put it correctly. Okay. Now here, when I take this EA by 2 inside, this 2 and this 2 will be get cancelled. So I have this 4 by 3 as it is. So I have 4 by 3 EA L cube, EA A2 L cube. Okay, this A2 as it is, and this L cube as it is, this 4 by 3 already taken outside. Okay, plus when I take this EA inside, so this 2, 4, and that it will be cancelled with this 4. Therefore, I have EA A1 L square minus this Q0 L cube by 3 as it is, Q0 L cube divided by 3 as it is. Okay, now here see, I have EA A1 L. Here I have EA A1 L square. So when I want to solve the simultaneous equation, I have to cancel some of the terms, but here it is not possible to cancel. For that, what I am going to do, this first equation I'll multiply throughout by L. So when I multiply this first equation throughout by L, what I am going to get? I will get EA1 L square plus EA2 L cube, because L square into L, it will become L cube, minus Q naught L cube divided by 2 is equal to 0 into L, it will become 0. So throughout equation, both left hand side, right hand side, I will multiply with L. Right hand side 0 is there, 0 multiplied by L, it will become 0. Okay. While writing the second equation, I'll just modify, or I'll just rearrange the terms here. So this term I'll take it first. So it is EA1 L square plus this term I'll take it second, which is 4 by 3 EA A2 L cube minus Q naught L cube divided by 3 is equal to 0. So now you can solve this equation, I mean these two equations, by changing the sign. This is positive here, both are positive. Therefore, now it will be changing to negative. This is positive here, I'll change it to negative. This is negative, I'll change it to positive. So EA A1 L square, one positive value, and here one negative value. This will be get cancelled. Then here what I have EA A2 L cube minus, because now this plus sign, now it is changed to negative. So it is minus 4 by 3 EA A2 L cube. Then next term minus, this is minus Q naught L cube divided by 2. Now this is negative, but now changes the sign to positive. So therefore it is plus Q naught L cube divided by 3 is equal to 0. Now what I can do is, here in these two terms, some of the common terms are there, like EA2 L cube is the common that you can take it. And here in these two terms, I have Q naught L cube is the common that you can take it outside. See, that simplification I do it here only. In these two terms, whatever the tick mark I have done, here I'll take EA2 L cube common. So if I take common, what is left out? It is 1 minus 4 by 3. That is what left out. That will be equal to, let us take this Q naught L cube by 2 onto the RHS, and this Q naught L cube by 3 is also on the RHS. When I take, this will become positive and this will become negative when I take it to RHS. And from both the terms, Q naught L cube, I'll take it common. When I take Q naught L cube common, it is 1 by 2 minus 1 by 3. So I'll write it once again here. So when I take Q naught L cube by 2 onto the RHS and Q naught L cube by 3 to the RHS. So, and after taking RHS, I'll take the common term is Q naught L cube is common term, I'll take it outside. So it is 1 by 2 minus 1 by 3. So next is what? I need this value of A2. Therefore, my A2 is equal to, can you tell me what the value of A2? After simplifying this, I hope everyone ready with your notebook, pen and calculator. See, my all class, you should be ready with your notebook, pen as well as calculator. Some of the values I will ask you to calculate. Q naught L cube 1 by 2 minus 1 by 3 is 1 by 3. Right? 1 by 2 minus 1 by 3. What is the value? 1 by 6, not 1 by 3, 1 by 6. This is 1 by 6. Similarly, EA L cube, what is 1 minus 4 by 3? Is it minus? You will get minus sign, no? Yeah, minus 1 by 3. Okay. So A2 is equal to, I'll get negative sign here. So this L cube will be get cancelled. So it is 3 Q naught divided by 6 EA. 2 is equal to minus Q naught divided by 2 EA. Now what you can do is, you can substitute this value of A2 in any one of the equation here, either in this equation or in this equation. Substitute the value of A2 in any one of the equation to get the value of A1. So I'll just show the substitution. Here, let us consider the first equation. I am going to consider this equation. This is the equation I am going to consider. EA A1 L square. So EA A1 L square, that I'll keep it as it is because now I have to find out the value of A1. EA A1 L square as it is, plus next term is EA A2 L cube. So EA A2 is minus Q naught divided by 2 EA, that is substitution I am doing, L cube. Then minus Q naught L cube by 2. That I'll keep it as it is, minus Q naught L cube by 2 is equal to 0. So in this entire equation, A1 is the unknown, you can find out. See here, this EA will be get cancelled. Now this is Q naught L cube by 2. You can take it to that side, Q naught L cube by 2. That also you can take it to this side. Both are negative, they will become positive. So I have EA A1 L square is equal to Q naught L cube divided by 2 plus Q naught L cube divided by 2. Because this is negative, when I take it to the RHS, it will become positive. This is also negative, when I take it to LHS, it will become positive. So here it is EA A1 L square is equal to Q naught L cube by 2 plus Q naught L cube by 2 is Q naught L cube. Correct? So therefore my A1 will be equal to, it is Q naught L cube divided by EA L square. EA L square on this side. So here L square and 1 L will be get cancelled. Therefore my A1 will be Q naught into L divided by EA. Now what is next step? And I'll come to the last step, fifth step. Fourth step is over, finding the value of A1 and A2. Fifth step is what? Finding the displacement. So I am finding the displacement here. So I'll come to the displacement equation. That is U1 is equal to, what is the U1 displacement equation here? Here U1 is A1 into L plus A2 into L square. So that I'll write down, U1 is A1 into L plus A2 into L square. So let us substitute both the values of A1 and A2. So this is A1. What is the value of A1? It is Q naught into L divided by EA into L plus what is the value of A2? A2 is minus Q naught divided by 2EA into L square. Correct? So U1 is equal to Q naught L into L, I'll take it as an L square divided by EA. Plus into minus, it will become minus. It is also Q naught into L square, Q naught into L square divided by this 2A, 2EA. This will be equal to, let us take a Q naught L square by EA common from both the terms. It is Q naught into L square divided by EA. I'll take it common. Then here 1 is left out, minus here 1 by 2 is left out. So 1 minus 1 by 2 is 1 by 2. Therefore, it is Q naught L square divided by 2E. This is what final expression. Q naught into L square divided by 2EA is the maximum extension which is there in this bar. That is what the bar is subjected to axial uniformly distributed load. If a bar is subjected to axial uniformly distributed load, this is the maximum displacement which is there in the member. It depends on the applied UDL, it depends on length of the bar, it depends on material, that is Young's modulus, and it also depends on the cross-sectional area. At any random distance, if I want to find out the displacement, that U is equal to, it is A1 into X plus A2 into X square. So A1 is Q naught into L divided by EA into X, this term into X, plus A2. What is the value of A2? It is minus Q naught divided by 2EA into X square. So what you can do, Q naught divided by EA, you can take it common from these two terms. L is not there here. Here L is not there. Therefore, I'll take only Q naught divided by EA common. If I take it common, what is left out here? Lx is left out. Plus into minus, it will become minus. What is left out here? Q0 EA already taken. X square by 2 is left out. X square divided by 2 is left out. So this is my expression. If any random distance, if I want to find out the value of displacement. Let us say if I want to find out what is the displacement exactly at the center of the bar, then I need to, what I need to do, I need to put x is equal to L by 2. If I want to find out what is the displacement or extension exactly at the center of the bar, then you put x is equal to L by 2. Wherever x is there you can substitute L by 2. Further you simplify, whatever the expression you are going to get, that is the expression of displacement at the center of the bar. Okay, now I'll go to the third problem. So once again it is RR method. Once again I have to find out the displacement. But here the bar is subjected to axial uniformly varying load. What is uniformly varying load? It is UVL. This is my bar fixed at one end, and this is subjected to axial uniformly varying load. Okay, so this is my axial uniformly varying load. So I'll tell you the difference between axial uniformly distributed load and axial uniformly varying load. This is Q0 per unit length. See, the difference between, see, sometimes what happens in the examination, he will say use the RR method and get the expression for the following system shown. Only this much he will say. He will not say whether it is subjected to UDL or UVL. What sentence he will mention? For the following system shown, find out the expression for displacement using RR method. Now you have to identify whether the bar is subjected to UDL or UVL. See, I will tell you how to identify. If the arrow marks are of same size, then I will say this is my UDL, subjected to UDL. Arrow marks are of same size. Suppose if arrow marks are goes on increasing like this, if arrow marks are goes on increasing, then this is what my UVL. See, that difference you should know, because in the examination purposely he will not mention whether the bar is subjected to UDL or UVL. It is identified based on the sizes of the arrow marks which are there on the all along the axial length of the bar. See, if you see the previous problem here, whatever the arrow marks I have shown, they are of all same size, same length. These are all of same length. Correct? Whereas in this diagram, I have shown the arrow marks are goes on increasing. Nothing but this is subjected to UVL. And once again, this bar is having an Young's modulus E and cross-sectional area A. Now, can you tell me what is the work potential? See, as I told, once again, it is a bar problem. Therefore, first step, if I start, I need to formulate the PE function, which is nothing but pi is equal to, it is strain energy plus work potential. So where strain energy, now as it is bar, so my strain energy is same, which is EA divided by 2 integration 0 to L. It is du by dx whole square into dx. So this is my strain energy stored in a bar. Now only thing is I need to find out the work potential, because now applied force is different. It is not a point force, it is not UDL, now it is a UVL. Now once again same principle you can apply. Let us consider a small element of length dx. I'll consider a small element of length dx. Now I need what is the force at this location where I consider the element. If I get the force, and let us consider the displacement at this location is u, because unknown, I don't know. But once again, what you can say, here my displacement is 0 and here my displacement is maximum, correct? No, once again, the displacement always is maximum at the free end and 0 at the fixed end. And at any random distance, I don't know what the displacement, that let us consider it as an u. Now what question comes here? I need what is the force on this element, or whatever the force acting where I have considered the element. That force multiplied by u will give you the work potential for that particular element. Then you put the integration between the limit 0 to L, means sum all the such elements, so that you will get the total work potential for that system. How to get the force at this location where I have considered element at any random distance? See, you have done this. UVL is nothing but, see, it is an axial UVL which is similar to your the UVL which is you are going to apply on the beam. Initially it is 0 and it reaches the maximum value. Now let us say here I have an element, in this location I have an element, and I want the value of force in this location. But what I know the force is 0 at this end and it reaching the maximum value at this end. But I want the force value at any random distance. What is this value? This is my Q naught, maximum value Q naught. And what is this? What is this? This is my length. Assume that it is distributed throughout the length of the bar. This is my entire length of the bar. This is maximum value Q naught. And let us consider this is the distance x where I have considered my element. So can you use the properties of two similar triangle here to find out the value of Q? Let us consider this is the value of Q at that location where I have considered the element, which is taken as Q. So how to find out this Q? So let us use the properties of two similar triangle. One is this entire complete triangle. Another one is, are you following? So the another triangle, whatever another triangle is, this triangle, you can consider this triangle. So if I use the properties of two similar triangle, what I am going to get? Can you tell me? What is that? It is Q naught divided by L is equal to Q divided by X, correct? No? So this value of Q naught divided by this entire length, and this value of Q divided by this length. Therefore, Q is equal to, it is Q naught into X divided by L. So this is the value of Q where I have considered the element. And this force multiplied by the displacement will give you the work potential. So that I am writing here, it is Q into X. So if I consider the force at this location is Q, if I consider force at this location is Q and displacement at that location is U, nothing but it is Q into X is what my work potential for that element, where Q in terms of Q naught is given by what? It is Q naught into L, I mean Q naught into X divided by L is what? Q naught by L is what? My force at any distance is X, and if I multiply this with U, then it will give you the work potential. It is Q into X into U. So Q into X is nothing but, it is Q is nothing but Q naught divided by L, this X as it is. And at that location, the displacement is U. If I write that U, therefore this becomes my work potential for that element. Actually, here it is Q into, I'll make it Q into U. So this I'll make it Q into U. So this is my Q into U, where Q is nothing but, Q naught into X by L, Q naught into X by L, and this U as it is. So this is my work potential for that element. Now I need work potential for the entire bar. So it is integration 0 to L. It is Q naught into X divided by L into U into dx, length of the element. Nothing but force. This is whatever the force, but I have not multiplied by the distance here. So you have to multiply the distance. Force into that distance I have to multiply. So that will change it. So here it is Q into U into dx. Okay. So it is Q into U into dx, where Q is nothing but Q naught into X divided by L. This U as it is, and that length of the element is dx. So if I put in for whole bar, so it is integration 0 to L Q naught into X by L into U into dx. Now further what you can do, it is once again whatever the work potential you are considering, all the work potential it is negative. And further simplification, if you want, you can do it. Now here Q naught by L, which is a constant, so that Q naught by L you can take it outside. Integration 0 to L, it is X into U into dx. X into what is that? X into U into dx. X into U into dx. Okay, so this is my work potential. So this is my potential energy equation. This is my strain energy, and this is my work potential. So now you can substitute equation number 2 and 3 in equation number 1 to formulate the PE function. So finally I'll write that formulating the PE function. It is EA divided by 2 integration 0 to L. It is du by dx whole square into dx minus integration 0 to L. Of course, Q naught by L I have taken outside. Q naught by L I'll take it outside. It is X into U into dx. X into U into dx is what my work potential for axial uniformly varying load. You need to substitute the value of U here as well as here. You need to substitute the value of U here and here. Before that, I'll go to the second step. That is assuming trial displacement function. You assume a trial displacement function. So what, once again I'll assume U is equal to, it is A naught plus A1x plus A2x square up to second order polynomial I'll consider. Then put the boundary condition when x is equal to 0, U is equal to 0. Therefore directly I'll get A naught is equal to 0. Now I'll not show all the substitution. When I put x is equal to 0, these two terms will become 0. U is 0. Therefore my A naught will become 0. Similarly, when x is equal to L, U is equal to U1 or Umax. U is equal to U1 or U is equal to Umax you can consider. Therefore, my U1 will be equal to, it is A1 into X or A1 into, directly I'll substitute with X value as L. So it is A1 into L. Same thing what you got done in the previous problem. So it is A1 into L plus A2 into L square. So similarly at any random distance, when X is equal to X, U is equal to U. Therefore, U is equal to, it is A1 into X plus A2 into X square. So to find the value of U1 and U, I have to substitute, or I should get the value of A1 and A2. Now after satisfying the boundary condition, I have to substitute the displacement function into PE function. That is what the third step. What is my third step? Substitute the displacement function into PE function. Now what I am going to get? Phi is equal to, it is EA divided by 2 integration 0 to L d by dx of U. U is nothing but A1 into X plus A2 into X square, that is my U, into dx minus Q naught by L as it is, integration 0 to L, X as it is. Now U is what? U is A1 into X plus A2 into X square. This is the value of U into dx. x into u into dx. Correct? No, my work potential is x into u into dx. Outside I have q naught by L. Same thing I have written. Outside q naught by L, x into u I replaced with this equation into dx as it is. Now once again, this is what? This is my entire square. So don't forget to consider that entire square because it is du by dx whole square is there. So this is du by dx whole square and this is a term. Now once again the simplification of the first term is same what you have done in the previous or previous to previous problem. Only this changes. Only this changes. So that I'll do the simplification. What is that? Q naught by L as it is integration 0 to L. This x I'll take it inside the bracket. Therefore it is a1 into x square plus a2 into x cube. I'll take this x inside the bracket. Multiplied by this x it will become square. Multiplied with this x it becomes cube into dx. Now you integrate this. So outside I have q naught by L as it is. So a1 as it is integration of x square is x cube by 3 plus a2 as it is integration of x cube is x raised to 4 by 4. Apply the limit 0 to L. Apply the limit 0 to L. Once again both the terms are consisting of x. Therefore I will not substitute the lower limit which is 0. I will substitute only the upper limit. So minus q naught by L as it is. It is a1 into L cube by 3 plus a2 into L raised to 4 by 4. Wherever x I will replace with upper limit L. Now in the next step what I will do, I will take this q naught by L inside the bracket. So it is minus. When I take q naught by L inside, this L and this 1 L will be get cancelled. Therefore I have q naught a1 L square by 3 plus into minus it is minus. Once again when I take q naught L, this L and here 1 L will be get cancelled, left out with 3. So therefore it is q naught into a2 into L cube divided by 4. And this side you know what is that equation? Pi is equal to, it is EA divided by 2. It is A1 square L plus 4 A2 square L square plus what is that value? Plus 4, sorry, L cube by 3 is there. Second term I have L cube by 3. Then it is 4 A1 A2 L square by 2. So I'll write that it is L cube by 3. It is L cube by 3. Then 4 A1 A2 L square by 2. This is a simplification of this first term. You'll get the same simplification. So only there is a simplification of the work potential you have to do, and before that you have to write the work potential equation correct. If you write the work potential equation correct and if you simplify, you'll come to that final position of P after simplification. Once if you get this equation, further is what the fourth step is you have to minimize PE. That is, you have to differentiate that with respect to A1 equated to 0, and you have to differentiate same PE function with respect to A2 and equated to 0. So if I differentiate first here, what I am going to get? Same thing what you have done in the previous problem. A by 2. What is that first term? It is 2 A1 L plus, because it is A1 square L is there. Therefore, if I differentiate, it will become 2 A1 L. Here 4 what is that? When I differentiating with respect to A1, this term will become 0. Here it is 4 A2 L square by 2. 4 A2 L square divided by 2 minus, when I am differentiating with respect to A1, this term will become 0. Therefore, it is Q naught L square by 3. So this is my Q naught L square by 3 is equal to 0. This is my first equation. Similarly, if I differentiate with respect to A2, what I am going to get? 4 2 A2 L cube by 3, correct? No? So this 4 as it is, differentiation of A2 square is 2A2 L cube by 3 as it is, and plus 4 A1 L square by 2 minus, it is Q naught. Here A1 is constant, A2 is 1, Q naught L cube by 4. So it is Q naught L cube divided by 4 is equal to 0. So these are the two equations you are going to get after differentiating. Now same thing. See, this simplification of first term, it is same. Only thing is only this work potential changes. So once again this EA I'll take it inside. So this two will be get cancelled. I have EA A1L, then plus this 2 into 2, it is 4, and that it will be cancelled with this 4. Therefore I'll get EA A2 L square minus Q0 into L square divided by 3 is equal to 0. This is my first equation. Similarly, this two will be get cancelled. 4 by 3, I'll keep it outside. 4 by 3, it is E A A2 L cube. This 3 already taken here. Then plus this 2 into 2, it is 4, and that 4 it will be cancelled with this. Then I have E A A1 L square minus this term as it is. This term I have to keep it as it is, which is Q0 into L cube divided by 4 is equal to 0. So these are the two equations I have to solve it as a simultaneous. But here it is EA A1L, here it is EA A1L square. Therefore, one L shortfall here. That therefore I'll multiply this equation by throughout L. Therefore, it is EA A1 L square plus EA A2 L cube minus Q0 L cube divided by 3 is equal to 0. Then writing second equation, I'll just rearrange the terms. It is EA A1 L square plus 4 by 3 EA A2 L cube minus Q0 L cube divided by 4 is equal to 0. So you solve these two equations as a simultaneous equation by changing the sign. These two are negative, this is positive. These two will be get cancelled. So I have EA A2 L cube minus 4 by 3 EA A2 L cube minus Q0 L cube by 3. Now this has become plus. So it is plus Q0 L cube by 4 is equal to 0. Now here once again in these two terms, whatever the common EA A2 L cube common, you can take it outside, and in these two terms you can take a Q0 L cube as common. Then here I have 1 by 3 minus 1 by 4 after taking to the RHS. Here same thing, 1 minus 4 by 3. So can you quickly tell me what is the value of A2 after simplifying this? After simplifying this by taking some of the terms common and sending this Q0 L cube by 3 and Q0 L cube by 4 to the RHS. What is the value of A2? The value of A2 written minus Q0 divided by 4 EA. Substitute this A2 in any one of the equation, either here or here, and get the value of A1. So first one is minus Q0 divided by 4 EA. Second one is plus, it is okay. Second is plus. This is plus 7 Q0 L divided by 12 EA. Okay. So you try to substitute the values of anyhow you have done calculation of A1 and A2. You substitute the value of A1 and A2 in U1 in the equation U1, get the final expression. So that is what I need to substitute here. Therefore U1 is equal to, it is A1 into L plus A2 into L square. So this is the U1 equation, that is maximum displacement equation, which is there at the free end. So A1, what is the value of A1 you have obtained? It is 7 Q0 L divided by 7 Q0 L divided by 12 EA. 12 EA is the A1 value into L, this L as it is, plus A2. What is A2? The value of A2 is minus Q0 divided by 4 EA. Minus Q0 divided by 4 EA into this L square as it is. So therefore U1 is equal to, further simplification, this L into L, it will be L square. So it is 7 Q0 L square divided by 12 EA minus, because plus into minus it is minus here, Q0 into L square. So here I have Q0 into L square divided by 4 EA. So this will be equal to, now what I will do, Q0 L square divided by 4 EA, you can take it a common term from these two. So Q0 L square divided by 4 EA, I'll take it common. Then what is left out? 7 divided by 3 minus 1, right? So 7 divided by 3 minus 1 is the term which is left out. So U1 is equal to Q naught into L square divided by 4 EA into 4 by 3 into 4 by 3. So this 4 cancels. Therefore, my U1 is Q naught into L square divided by 3EA. So this is the final expression for U1. So it depends on the applied UVL Q naught, then length of the member square, and Young's modulus and area of the bar, what I have mentioned. Okay. Similarly, you can do it for any random distance. U is equal to it is A1 into X plus A2 into X square. So A1 into X plus A2 into X square. Only thing is, once again, I need to substitute the value of A1 and A2. That's all. Same thing what I have done here. I need to do that. That is 7 Q naught L divided by 12 EA into X plus of minus Q naught divided by 4 EA into X square. Okay. So further simplification. See here, I have L here, but whereas here I don't have any L. So Q naught divided by 4 EA, you can take it common. So Q naught divided by 4 EA, if you take it common, what is left out here? 7LX divided by 3 minus this term already taken, so left out is X square. So this is the expression for any random distance, where if I substitute the value of X, say, for example, if I want to calculate what is the extension exactly at the center of the bar, then you substitute X is equal to L by 2. Wherever X is there, you substitute L by 2, you'll get the expression for center. If you want the extension at the extreme end, see, I'll get the same equation. When you substitute X is equal to L, I'll get the same expression. You can try that. Okay, so this is a general form where you can put any value of X and you can obtain that displacement at that particular location.
Okay, guys, we will solve one more problem on RR method in the next class. Then we will switch to the beam problems using RR method. Thank you for watching. Please like, comment, share, and subscribe the channel.